Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the next chapter of AC analysis, which is the most important chapter for EC guys as well. I'm telling you guys, mostly questions are framed from EC, right, in resonance only. This year also one question came from resonance only. I'm talking about gate 2024. So yeah, so we will start with resonance. So you can see this graph. Okay, somewhat I have taught in control as well. So we will see more about this in deeper, go more deeper into this. Okay, so before going, obviously we have to understand what is resonance, what are the simple things. So we will start with the series resonance circuit. What is series resonance circuit? It is simply a series RLC circuit. I have all the components. The most common circuit which you will see for resonance is the series RLC. So what is resonance? Like there are many definitions of resonance which you will learn slowly as we move along the chapter. So first definition is resonance occurs in an electrical circuit when energy oscillates between inductor's magnetic field and the capacitor's electric field. So like they are very fancy words, right? Energy oscillates between inductor's magnetic field, capacitor's electric field. Oh my god, what is happening? What is happening? So this phenomenon is known as resonance. How is this happening? I will prove it to you. Okay, don't worry, don't take the stress, give the stress to me. I will prove it to you. How is energy oscillating between the inductor and capacitor? I will show you. Okay, for now just understand this phenomenon happening at a certain frequency is actually known as the condition of resonance. This phenomenon is transferring of energy from magnetic field to electric field. As the energy oscillates, this phenomenon is known as resonant, and the frequency at which it happens is known as the resonant frequency, also known as the oscillation frequency. When it happens, actually, it happens when my load, another definition of resonance is my load demands, my load demands only active power. Okay, my load demands only active power. Now let's discuss when it happens. When does your load only demand active power? Who consumes active power? Resistor, right? That means your load is purely resistive. Your load is purely resistive. Only in this certain condition resonance will happen. When you, like, there are many conditions, right? All of them point to the same thing only, but there are three conditions, like many conditions. They are saying the same thing basically. Either your energy is oscillating from magnetic field to electric field, or your load is demanding purely active power, or your load is purely resistive. So when it happens, when does your load become purely resistive? So what is the impedance seen by the source? Zn is, it is a series circuit, right? It will be simply R plus J XL minus XC. This we have taught in the, learned in the phasors. This we have already learned in the phasors. So how will this become purely resistive? How will my input impedance become purely resistive? This will only happen when this component is 0. Then only my impedance will be purely resistive. Okay, so that is my XL is equals to XL minus XC has to be equals to 0. That means XL is omega L equals to 1 by omega C. So at a particular frequency that is known as omega naught or omega R, resonant frequency, this will be equals to 1 by under root LC. The most famous equation. I know you already know about this thing, right? So this, right, is the very basic thing. I think you already know. Okay, so here like what this frequency, right? If I take this omega here, this will be omega naught whole square divided by omega by LC. So this will be omega naught will be equals to 1 by under root LC. Okay, so this is the resonant frequency. This has been derived. Very simple, very straightforward, nothing to worry. And I know you already know about this. You have already know about this. So what are the other things that happens in resonance? what are the other things that happens in resonance. So if I apply a KVL in this whole loop, I see I have this input V plus VR, all of them are phasor only, plus VL plus VC equals to 0. Okay, so this will be V equals to VR plus VL plus VC. Okay, this is my input voltage basically. This is my input voltage. Now I can write this in phasor. If you remember, this is basically with respect to the initial voltage, this is 90-degree leading and this is 90-degree lagging, right? I hope you remember all these things. These are in your head, right? And VR is just in phase, right? This is like VR angle 0, same phase. So your V is equals to VR, the real part, angle 0, plus J VL minus VC. Okay, so in resonance, one more thing happens basically is I can write this further, right? This is what is V? V is I into Z, correct? I into impedance. This is equals to I into R plus J I into XL minus I into XC. So Z is R plus JX, that I know. But from there, what I can say is XL is XC, right? XL is XC. So if XL is XC, these two are same. So if these two are same, basically, that means what? That means they will cancel each other. Because I is common and XL is equals to XC, that means this will be 0. If this is 0, that means this will be 0. That means in resonance, the voltage across the magnitude of the voltage across the inductor and the magnitude of the voltage across the capacitor is same. Their phase is different. Phase is this, right? Minus J plus J. Phase is different, but the magnitude of voltage across the capacitor and magnitude of voltage across the inductor will be same. In resonance, the magnitude of voltage across the capacitor and magnitude of the voltage across the inductor will be same. Of course, voltages will not be exactly equal because there is some phase difference, but magnitude will be same. I have proven here. Got it? So these are few what I can say points, right? Conclusions of series resonance circuit that you must keep in mind, because whenever a circuit, like in the question, right, there will be some resonant condition and then you have to solve the circuit you just pick up the gate 2024 question, resonance question, network theory. Okay, like there was a circuit and it was actually in resonant condition. So whenever there is a resonant condition, multiple things can be happening due to resonance. So you have to it's better if you understand these things and if you keep in your mind what are the things that happen, what is happening. Okay, so next is about the basically what I told, right? Then imagine basically my voltage will be, input voltage will be purely resistive, that is VR of 0. So the resistance voltage will be equals to the input voltage only. That is my imaginary part of the supply voltage will be 0 because there will not be any imaginary component, because my load is only asking for active power. So imaginary component will be 0. That's why VL will be equals to VC, and from here also you can derive the same thing only, that I into XL will be equals to I into XC. From there also you can derive the same thing, that is omega naught equals to 1 by under root LC. So from here I can write I into XL equals to I into XC, or I will get cancelled, XL equals to XC. So omega naught whole square will be equals to 1 by under root LC, or omega naught, sorry, omega r. Okay, so remember omega naught whole square is 1 by LC. This is very helpful. This multiple times can get used. So remember this, right, is in radian per second. So don't get confused. This is in radian per second, but I can write this in 1 by 2 pi under root LC. So this is in hertz. Okay, so there are two things here. First one is omega naught and second one is f naught. This one will be in hertz only. This one will be in hertz only. Okay, This will be in hertz. Got it? So this is omega naught, this is hertz. That is fine. So I hope things are clear now. Now let me have I drawn the phasor diagram. So phasor diagram is not here actually. Okay, so let me draw the phasor diagram. Basically, if I draw the phasor diagram, that basically my Vs is here, right, or my I is here. So I is the reference, right, because it is a series circuit, series RLC circuit. I is the reference. Okay, and my VR will be in the same phase as I, because it is a resistive, it is resistance. So VR and I will be in the same phase. Basically, this will be VR. And in resonance, where is my VL? VL leads the current by 90 degrees, correct? This is what my VL does. So VL will be somewhere here. Okay, and this is my VC. VC lags the current by 90 degrees. Okay, so the magnitude of VL and VR are same, but their phase is totally opposite. So of course they are cancelling each other out. Ultimately Vs, right, is the sum of all phasor, sum of all of these components. So ultimately it is simply in phase with the current only. So from the phasor diagram also you can see that what is my Vs. From the phasor diagram also you can see what is my Vs basically. Okay, so yeah, this is the phasor diagram basically. Now what else can we say, what else can I comment upon? So next what I can comment upon is that about the impedance. So one thing is very conclusive, that the supply voltage and the supply current both are in the same phase. If they are in same phase, that is my power factor is 1, it is a unity power factor. That means my power factor angle, it is equals to cos phi. So what is my phi? Phi will be 0 because there is no phase difference, phi 0. Okay, so this is one of the conclusions of resonance. So at resonance what happens, I get unity power factor. Why? Because it is a purely resistive circuit, and if it is a purely resistive circuit I will get a unity power factor, right, purely resistive circuit. Okay, so what about the series, what is happening with the impedance and all those things, right? So now we will plot the graph of individual components, then ultimately I will talk about, I will discuss about the impedance. Okay, so individually if I vary my omega frequency, what will happen to R? R is just a constant number, resistance is independent of frequency. For our case resistance is independent of frequency, so it will basically be a straight line, it is constant value, correct? Okay, what about the inductance? What about the inductance? So if I increase my frequency omega, omega L increases linearly because XL is directly proportional to omega, correct? It is varying linearly. So if I increase my frequency, my my inductive reactance increases linearly. Okay, inductive reactance increases linearly, correct? What about the other part, the inductive capacitance, the capacitive reactance, not the inductive capacitance, what I am talking about. Like this happens when you are not sleeping and recording whole day. Okay, this is what happens. So what will happen to the capacitive reactance? So capacitive reactance, if I see capacitive reactance, I will just take the blue color. Capacitive reactance is basically inversely proportional to omega. Capacitive reactance is inversely proportional to omega. Okay, so how is the graph? I'm not talking about the magnitude for now. Okay, just sorry, I'm not talking about with the sign, I'm just talking about the magnitude for now of capacitive reactance, right? I'm not taking into effect the sign and phase. I will take into effect, don't worry, I will take it into the effect. So it is just like a hyperbola, right? Because a hyperbola is also inversely proportional to its function, its value. So this will be somewhat like this, somewhat like this. Okay, it will vary somewhat like this. So these are all the values. Can you write the magnitude of Z or impedance? So this is R square plus omega L minus 1 by omega C whole square. Okay, what about the angle basically? What about the angle? So the angle is tan inverse the imaginary upon the real part. Imaginary is this omega L minus 1 by omega C divided by the real part. Now assumption is obviously the angle will be between minus 90 to plus 90. So either I am in the first quadrant or second quadrant. So depending on the sign, right? If this is negative, this will be negative. If this is positive, then this will be positive. Got it? Got it? Basic, right? Basic. So that's why if you have doubt, please go back to the basics. Okay. Now what is happening at resonant frequency? At resonant frequency, XL is equals to XC. So omega L equals to 1 by omega C. So this is 0. So phase of impedance is 0, and that makes sense, right? Because we have told you it is purely resistive circuit. So obviously for a purely resistive circuit, the impedance angle is simply 0. And what is the value of the impedance at that resonant frequency? It is simply R, and this is the minimum value. Because of course if there is some finite value here, if this is not 0, if I square it then add it, it will increase, it will only increase. So minimum value of impedance is this one only, minimum value of impedance is this one only. Okay, this is the minimum value of impedance. Okay, so now what we will do, we will actually plot magnitude of Z, we will plot the impedance. So for plotting the impedance, right, basically what we are doing, we are adding all these three, right, we are adding all these three. So initially if you observe, this is, let's take a number initially at t omega equals to 0.1, this is let's say 1 ohm, this is 0.1 only, or let's say L is 1 Henry, so this is 0.1 only, and it is what, 10, let's say C is 1 farad, so 1 by 0.1 is 10. So initially capacitance is dominating, it has capacitive behavior. So if initially capacitance is dominating, what will happen, I will just okay, I will draw it basically. Okay, just a weak capacitor. Okay, we will draw two graphs, one will be here, one will be here as well. Okay, okay, so this will be omega, this will be omega, okay, and this will be magnitude of Z. So I'm plotting the magnitude of the impedance basically. So I want to see one thing. Okay, this is not there. Okay, so basically, right, initially I told you it will, like, capacitance has the highest value, so capacitor will dominate. So initially capacitor will dominate. If I copy the graph, right, if I copy this graph and paste it here, okay, so initially whichever one is the higher value, that will dominate. So initially it is like this is the for the capacitor one, and this is the inductor one basically. Okay, this is the inductor and this is the resistor basically. So of course, and they will have an intersection point exact at that point basically XL will be equals to XC. So ultimately my impedance will become R only at that intersection. At what frequency? This happens at my impedance, right, at omega naught frequency. So this side will be the intersection point. Okay, so this is the intersection point basically, omega naught. Okay, so ultimately initially this is higher value, so this will dominate, and then in the middle at omega naught both are equal, so it is purely resistive. After it, right, L increases, omega L increases, so of course it will be inductive because inductance will dominate. From here also you can understand, right, if omega no, omega is lower, so 1 by omega will be higher, so initially it will be capacitive. Then as omega increases, 1 by omega will reduce, this value will increase. So if this value increase, so it will be inductive. Very simple, right? So I will write here in brackets in a table basically that my omega and what is the circuit behavior basically. So this is my omega here, circuit behavior here. So circuit behavior is here, this, right, I can further increase and reduce the size here. Okay, circuit behavior, don't mind if my spelling is wrong. I'll check the spelling. Okay, I'll check the spelling of behavior. I think it is OUR. What I remember, it is OUR. Let me just cross verify this. Else, you guys will not, you guys will just not give me a favor, right? Behavior, yeah, it is correct. VIOUR. So, circuit behavior is here, and this is basically the power factor. So, initially, right, for low values of omega, when my omega is less than the resonant frequency, that is, I'm going towards the resonant frequency. If it is less than resonant frequency omega naught, circuit behavior is capacitive. Why? Because of course, right? Why? Because capacitance has higher value. 1 by omega naught C will be higher, so that's why. So 1 by omega naught C will be dominating, so it will be capacitive basically. Circuit behavior will be capacitive. What about for a power factor? So power factor will be leading. If it is capacitive, power factor will be leading basically. Okay, omega equals to omega naught, and at omega equals to omega naught, you know, right, it is the condition of resonance, so it will be purely resistive. And this will be unity power factor. Okay, and at omega greater than omega naught, it will be purely inductive. Okay, and the power factor will be lagging basically. Got it? So of course, like this you can understand from here as well. Here in this region it will be lagging, in this region it will be leading, and of course in between it will be purely resistive at this point. purely resistive. Okay, so ultimately, right, your graph will be somewhat like this. It will not be exactly like a few teachers I have seen, they draw this exactly something like this. It's like symmetrical, right? About omega naught it is symmetrical. No, but omega naught it is actually not symmetrical, because like this is not proper like parabola or something like that, right? This is some hyperbola. So what will happen, it will be tilted basically. So this, right, it will be linear as omega is increasing. As omega is very high, my circuit almost is purely inductive. How? Let me take few values, right? You will understand. So let us take few values. Let me take L equals to C. L is 1 Henry, C as 1 farad, and R as 1 ohms. Let me take few values. Omega equals to 0.01, omega equals to 1, omega equals to 100. Can we write down the impedance? So here it will be what? R plus JXL. So R plus JXL minus XC. So R is 1 ohm, it is constant always, plus JXL. It is omega into L. L is 1, so it will be 0.01 J minus 1 by omega C. 1 divided by omega C. Omega is 0.01 and C is 1 only. So this becomes what? This roughly, this is what? 0.01 minus 100. Who is bigger? Obviously this one. That's why I told you, right? It will behave as a capacitor. So this will be plus minus J 100.01 roughly, right? It is almost minus J 100 only, because you can ignore this one. Okay, same, you just put this value, same analysis you do for omega equals to 1, omega equals to 100, you will understand what I mean. Okay, so if omega is very high, it is inductive. So for inductance, right, it is linearly proportional. So my graph will be almost linear in nature. If omega is very low, it is capacitive. So my graph will be hyperbolic in nature. Okay, that's why it will not be symmetrical. Many educators, they teach this thing wrong. Okay, they tell you that it is symmetrical. No, it is not symmetrical. It is not symmetrical about the resonant frequency omega naught. Okay, so this will be, I not able to do this. Okay, how to change? Yeah, so this is the frequency, resonant frequency. Okay, and this is the impedance basically. Okay, and again marking out that on the left hand side it is capacitive, on the right hand side it is inductive, on the middle omega naught, not at the middle actually, uh, basically at omega naught frequency it is resistive. Okay, got it. So this was about the graph, very simple thing to explain. Now I will come to the current. Basically current is what? Basically current, right? Because I have a single voltage source, magnitude of current is basically magnitude of voltage divided by magnitude of the impedance, correct? So voltage is some magnitude of voltage is constant, right? Magnitude of voltage is constant, it is not varying basically here, right? Here is the voltage signal. If you see, here is my voltage signal. Magnitude of voltage, amplitude of voltage is not changing. Amplitude of voltage is not changing. So I can say that it is equals to V by magnitude of Z. V by magnitude of Z. So it is equals to what? It is equals to magnitude of V divided by magnitude of Z. So magnitude of V is what? Magnitude of V is constant divided by the magnitude of Z. So Z is varying with respect to frequency. This is constant. So I can write this as magnitude of V is Vs divided by magnitude of R square plus omega L minus 1 by omega C whole square. Okay. So ultimately what you can see is initially, right, the impedance is very high. If you see initially For lower values of frequency, impedance is very high. If impedance is high, automatically your current will be very low. So it will be almost zero, right? Because finite upon infinity is zero. So that's why this is zero. Now, as we move along, what happens? The impedance reduces and it becomes minimum at XL equals to XC at resonance frequency. It becomes purely resistive. So that's why you see the current is peaking because impedance is minimum at omega naught. That's why the current is peaking. Then after this omega naught point, again the impedance increases because the behavior is inductive. So if impedance increases, the current will automatically reduce because Vs is constant. The denominator is increasing. If denominator increases, the current will reduce. Okay. Now there are few important points. So what are the important points? First point is this one, at omega equals to omega naught. Now there are two other points on the graph, omega L and omega H. Okay, so they are actually called as the 3 dB points or the cutoff frequency. Okay, so they are called as the 3 dB points. Okay, they are called as the 3 dB points basically. So why is it called 3 dB points? Why is it called 3 dB points? Basically, right, we identify this is the peak of the current, right, maximum value of the current that my current can reach, because this is the point of peak. After that it will only reduce. So peak is V by R. So from the peak, if I multiply 1 by root 2, 1 by root 2 is very very important number. Why? I will discuss. Okay, if I multiply a factor of 1 by root 2, the points at which the current is 1 by root 2 times the peak value are the 3 dB points, or also known as the half power points. Half power points. So as the name suggests, we get the half power of the maximum possible power that I used to get in resonance. So these will be my half power points basically. Okay, this will be my half power points. Got it? So, and why is it called 3 dB? 3 dB, right? If a number is in decimal scale x, and if I want to convert this in dB scale, you do 20 log base 10 x. Okay, so x, let's say, is 1 by root 2 because I am multiplying by a factor of 1 by root 2. This will be 20 log base 10 1 by root 2. If you do this, right, you will observe it is minus 3 dB. That's why it is called as the minus 3 dB down. So if I will do in front of you. So under root 2 into log into 20. So it is minus 3 dB approximately. So it is minus 3 dB. 3 dB. Why is it minus 3 dB? Because it is 3 dB down, right? 3 dB down from the peak. Decimals, 3 decibel down from the peak. Okay, so that is the case basically. That is the case here. So that is why these half power points are important. We will obviously calculate when does it happen. When does it happen? We will obviously calculate that thing. Okay, so like and the difference between the higher cutoff frequency, half power point frequency, and lower cutoff frequency, these are also known as cutoff frequency, is known as the bandwidth. This is known as the bandwidth of the circuit, because after this, right, the power will go down even further because the current is going down. So ultimately no signal is getting passed through the circuit. So if no signal is getting passed, so we say that for certain frequency, for certain bandwidth, it will pass the signals. Everything other than that bandwidth, it will not pass. So it is the bandwidth of the circuit. Okay, like that. So this, right, will be cleared more in filters, and where you study filters in signals and systems or analog electronics. So this will be cleared there about bandwidth, physical significance of bandwidth. So like definition, I will obviously say what is the definition of bandwidth. So the definition of bandwidth is basically the bandwidth refers to range of frequencies where the signal remains above the half of the maximum value, not half, sorry, half of the maximum power basically, not value, sorry, maximum power. This will be maximum power. Okay, half of the maximum power. So omega L is the lower 3 dB frequency and this is the higher minus 3 dB frequency. These are known as minus 3 dB frequency. Why higher and lower? Higher basically means it is the higher of the two, because initially you reach peak. Of course, you can start from lower to higher, then go from higher to you can go lower. So I will cut this I max by root 2, right, twice in my whole journey. I will cut this I max by root 2 twice. So one will happen after resonant frequency, one will happen before resonant frequency. So the one which happens after resonant frequency, that is known as the higher 3 dB minus 3 dB frequency omega h, and the one that happens before resonant frequency is known as the lower 3 dB frequency, that is omega L. Got it? So this will be omega h and this will be omega L basically. Okay, so these are the higher and lower, and the difference between those two, because after this omega h and before this omega L, of course power will be lower than half. If power is lower than half, then of course that will not be the, like, that will not pass the signal. So if you want to pass the signal, we have to pass within the bandwidth range. Bandwidth is omega h minus omega L. This will be discussed more in the next lecture. Okay, this I will discuss more about the next lecture. Power, I hope you know, because we have learned power. Power is simply I square R, right? Power is simply I square R. So in resonance what is happening? So what is the bandwidth? Bandwidth I will discuss later. What is the power at resonance? So in resonance, right, let's say the power is basically what? It is a purely resistive circuit. So if it is a purely resistive circuit, what is my I of t? I of t is simply Vm by Vm sin omega t divided by R. Okay, Vm sin omega t divided by R. So can you find out the power? Power is very simple, right? So like power is, this is the voltage or the current signal. Power will be what? Irms whole square into R. So it will be voltage divided by current. Yes, so it will be Vm by root 2 R whole square into R. So this will be Vm square divided by 2R. Okay, Vm square by 2R. This is the power basically. So what happens basically in half power frequencies? The power is halved. At 3 dB frequency, this is the power at what? At resonance. At omega equals to omega naught. So the power, active power delivered at half power frequencies will be what? Basically P 3 dB will be what? Half of the maximum power. This is the maximum power, right? Why? Because the impedance will be lowest. If the impedance is lowest, current is maximum. You see, current is maximum, right? And power is what? Irms whole square into R. So current, wherever the current is maximum, at that point only the power will be maximum. Okay, so because power is Irms square into R. So at 3 dB points it will be half, right? P omega naught divided by 2. So it is Vm square divided by 2R divided by 2. Okay, Vm square divided by 4R. Vm square divided by 4R. So that is basically the 3 dB power. Can you find out the current here? What is the Irms? Irms, it is equals to Irms whole square into R. This formula will not change, right? Power formula will not change. So what is Irms here? This is Irms at omega equals to omega 3 dB, right, or omega L or omega H. Okay, so from here I can find out the IRMS, that is equals to what, at frequency, like current is a function of frequency, either omega L or omega H. This will be simply Vm by 2. Okay, this will be Vm by 2R. And what was my initial RMS current? Initial RMS current was Vm by root 2R. So if I find out the ratio, right, I 3 dB divided by IRMS or I omega naught, what is this? It is simply 1 by root 2. So my I 3 dB is simply I omega naught, or the current at omega naught divided by root 2. What is I omega naught? It is Vm by root 2. So it is Vm by 4, Vm by 2 basically. Very simple. So that is what I have written here, right? V by root 2R. Why? This is the peak value V by R, and if I divide by root 2, I will get the cutoff frequency currents. So at cutoff frequency, the power is half. Okay, these are the half power points. Power is half of its maximum value, but the current is 1 by root 2 times. So at half power points, power is half. Okay, power 3 dB will be P omega naught divided by 2, but the currents, right, currents I 3 dB equals to I omega naught resonant current divided by root 2. It is not exactly half. It is not exactly half. Okay. So these are the few things that you need to like keep in mind, and we will discuss more about this bandwidth, higher frequency, lower cutoff frequency, more about this later on. So few conditions of resonance. At resonance, a series resonance, basically the impedance is the minimum at resonant frequency, the current is the maximum because current is voltage by impedance, and as the current is maximum, power is IRMS whole square into R. So your power also will be maximum. Power will also be maximum. Power will be maximum. Okay. So these are the things that happens basically. This we have already discussed, right? This we have already discussed. This 3 dB also I have discussed. It is basically either 1 by root 2 times of the peak current or 70.77%. Same as this is same as this 1 by root 2. If I convert this into percentage, it comes out to be 70.7%. Okay. These basic things are clear. This resonant frequency is cleared. This is in hertz, radians I have already discussed. So don't get confused, right? Don't get confused between hertz and radians, because this is 1 by root LC, this is in radian per second, and this unit is in hertz. So don't get confused. It depends in what unit they are asking. So please don't make this mistake. So now we will actually calculate the higher and the lower 3 dB frequencies. Now let's calculate the value of omega H and omega L. So what do we know that happens at these frequencies, omega H and omega L? Basically at these frequencies, my current magnitude is the under root 2 of the maximum, right? This is what happens. So what is Imax? Imax is basically Vmax by R, correct? Because at the current is maximum when the circuit is purely resistive, and then the impedance is simply R. So it will be Vmax divided by root 2 R. Okay, that will be my magnitude of current. So this, right, is actually, what is the magnitude of current actually equation? So magnitude of current equation is ultimately it is equals to what? V max divided by the impedance, correct? magnitude of impedance. That is what that is the magnitude of current. So it is V max divided by under root R square plus omega L minus omega C whole square. Okay, so from here you can directly comment that basically it is equals to what, V max by root 2R. So ultimately V max cancels each other out. So basically if I square both sides, 2R square is equals to R square plus omega, like my omega L minus 1 by omega C. Okay, this is the at the frequency omega either equals to omega H or omega L, any of the frequencies, right? Now one interesting fact will be there. Actually I will discuss about that fact. So what is the equation I get? I get omega L minus 1 by omega C whole square is equals to R square, correct? I hope you are understanding, right? I am just equating these two. If I equate simply V max will be cancelled, then I am squaring both sides. So this will be 2R square, and if I square this will be R square plus omega L minus 1 by omega C whole square. Now omega L minus 1 by omega C whole square is equals to R square. This is my equation. I can further write this. I can take the under root of this, right? I can take the under root of this. If I take the under root, information will get lost. What information I will discuss? If I take the under root, this will be omega L minus 1 by omega C equals to R. If you are writing this equation, that means you have not studied 11th and 12th properly. Okay, you have not studied the chapter quadratic equation, because if I take the under root, right, there are two solutions basically here. This can be plus minus R. Why? Let's say I want to, from this equation I want to go back to this equation. How do I go back? I have taken the under root, so I have to square this, then I will go back to this equation, right? So if I square this, the left hand side is okay, omega L minus 1 by omega C whole square, that is fine. But what about the right hand side? Will it satisfy only for plus R? For minus R also if I square, will I get R square? Yes. So this, right, satisfied for minus R as well and plus R as well. So I will get two solutions here. What are the two solutions? One is the omega H, another one is the omega L. Those are my two solutions basically. So it is basically a quadratic equation. How is it a quadratic equation? Very simple, right? How is it a quadratic equation? Simple, right? It is basically omega square, quadratic equation in terms of omega square minus 1 by LC equals to plus minus R by L. Okay, if you solve this quadratic equation, you will find the value of omega. Okay, you will find the value of omega. That of course I will derive that one. But more important than that is this equation. This equation is very important. This equation, I will tell you, it's good if you remember it. Of course I have derived and you understand like how are the values coming, but if you remember this will be helpful. So basically, right, there are two solutions. So when it is equals to plus R, that means what? If it is equals to plus R, this is what actually? This omega L minus 1 by omega C, this is what? This is XL minus XC, correct? So if it is plus R, that means it is positive. If it is positive, that means XL minus XC is positive. So in this case, in the positive case, so if I write this, right, this will be, one of the solutions will be 1 omega L by 1 by omega C equals to plus R. Okay, so XL minus XC is positive, XL is greater than XC. So what does it mean? Basically it means that circuit is inductive. Basically. That is what it means. Okay. Another important point, I will also talk about the other solution. What is the other solution? That is omega L minus 1 by omega C is minus R. If it is equals to minus R, that means what? If it is equals to minus R, that means basically this is higher than this, then only I will get some negative value. That means it has a capacitive behavior. So my circuit is capacitive now. Okay, I have a capacitive behavior, so my circuit is capacitive now. What is the angle? So the angle formula, if you remember, of impedance, right? Angle is what? It is equals to tan inverse omega L minus 1 by omega c divided by r. So this will be equals to uh, now when this value, this is what, xl minus xc, xl minus xc. So when this value is plus r, that means it is tan inverse plus 1, right? So there are two cases here. One case is when it is plus r, so it will be tan inverse 1, that is when my xl is greater than xc, so it will be tan inverse 1, that is 45 degrees. Impedance angle will be plus 45. When it is minus r, it is leading, that is my xc is greater than xl, that means it is minus 45 degrees. Makes sense, right? Impedance angle will be negative for leading loads. Makes sense, total sense. Okay, so this was basically the short description about the capacitive behavior and inductive behavior. So this formula is very important, although I don't tell you to remember, but this is an important thing. It's good if you remember, right? It will be helpful. Basically, it will be helpful if you are able to remember this thing. Okay, now let's basically derive the value here, right? So I was here basically, yeah, I was here somewhere, yeah, this if I copy. So let's solve for the two cases. So I know that if this is plus r, that means my behavior is inductive. And when do I get inductive behavior? When I am greater than omega, omega naught, omega is greater than omega naught. So this is the region where my circuit behaves as inductive, right? So this is the omega h basically. Omega h is here somewhere. So at this region, the impedance at this particular point, the impedance provided by it is R plus JR, because R is the reactance also, because XL minus XC is equals to R plus R. So that's why this will be plus R basically. This will be plus when it is omega H whole square. If I replace omega to omega H, this will be plus R, and the explanation also I have given. And this will be omega L, basically it will behave as a capacitive when it is minus R, R by L. Okay, so now if I find out the values, so omega H minus, okay, something I have done a bit wrong, because I think there here also there will be omega, right? Yeah, I messed up. This also will have a omega, right? If I'm multiplying by omega on both sides, this also will have a omega. So this also will be omega H. This also will be omega L. Okay, so omega H whole square minus R by L omega H minus 1 by LC equals to 0. So ultimately the solution of this root, omega is minus B plus minus B square minus 4AC. Okay, so this, right, I don't generally say students to remember. What I tell students is to remember this equation. This one is very important equation. This one, right, I will say it's okay if you don't remember, right? It's fine because this remembering this is very difficult, so I will not say you to remember this formula. Okay, so divide by E is what, 1. Okay, so this is the formula that you get basically here. 4AC B square by 4AC. Anything am I doing missing here? No, it is correct only. If I take this, take it as common, will not be able to take it as common. So somewhere someplace I'm doing something. No. B square minus B plus minus B square minus 4AC divided by 2A. Okay. This will be 2, right? Okay. I am also forgetting the quadratic equation. So my class 10 is also weak. So we have to improve our class 10 as well. just forgetting something. So again, same for omega L as well, same for omega L only, not much will change. So omega L is equals to R by L. So this, right, this equation will be what? This equation will be plus omega L minus 1 by LC equals to 0. Okay, so this omega L equals to omega L will be equals to minus R by L plus minus B square minus 4AC, B square minus 4AC. So B square is R by L whole square minus 4, or this will be plus LC divided by 2A. Okay, so from here, which solution will you choose? Okay, because there are two solutions, right? Which solution will you choose? So of course your omega H and omega L cannot be negative. Omega H and omega L cannot be negative. So this number, right? So let us first clear few things. So this omega H will come out to be, if I divide by 2, right, this will be R by 2L plus minus divided by 1 by LC. Okay, and omega L will be equals to minus R by 12 plus minus under root R by 12 whole square plus 1 by LC, because I have divided by 2. So what we notice is this is R by 12 whole square. I am adding something with it. Then I am taking the under root. So it will be somewhat more than R by 12. It will be somewhat more than R by 12. So I cannot choose the negative values here. Negative values I cannot choose. If I choose negative values, right, overall you will see, you will observe that overall your frequency will come negative, and obviously you know negative frequency is not possible. So we will ignore the negative frequencies, because negative frequency is of course not possible. So from here this beautiful equation is derived, that is omega H, that is had 3 dB frequencies R by 12. If you can remember this, that will be good. If you don't want to remember, then it's also fine, but it's good, right? The toppers do remember this formula, that is R by, like this R by 12 also has a name, I will explain. And of course this is what, this is 1 by under root LC whole square, right? And what is 1 by under root LC? Omega naught square. So I will come to the main formula that I want you to remember. I will come to that. Omega L is minus R by 12, okay, minus R by 12 plus under root R by, so this is whole square, right? R by 12 whole square plus 1 by under root LC. Okay, so now what we can comment is, there is the relation that I told you, right? What is bandwidth? Bandwidth is the difference between the higher cutoff frequency and lower cutoff frequency, omega H minus omega L. So don't worry if you don't know the physical significance of bandwidth. This will be cleared in analog electronics and in signals as well. So basically in the filters chapter. So omega H is this, omega L is this, correct? What is common? This part is common basically. So if I subtract, the common part will go away. This will be minus of minus r by 12, so this will be plus r by 12 and this is r by 12. So ultimately this comes out to be r by L. Bandwidth is r by L. What is the unit? What is the unit? Unit is radian per second. If they ask in hertz, how will you write? Sometimes they define bandwidth in hertz as well. What will you do? Divide by 2 pi. You will divide by 2 pi. Okay, trust me, you will make a mistake. Okay, here you will make a mistake, trust me. In the examination hall, it will be a question of resonance, very simple question. It will be a question of bandwidth, but at the end, right, the unit will be hertz and you will not remember. You will just write, sir, I put the formula correct, r by L. Yeah, I did everything correct. Okay, then as you come to the after you came from the exam hall, right, you are seeing like educators solving the question. You're saying, यार सबका अलग क्यों आ रहा है यार, मेरा तो वो सही है, r by L. Everyone is saying this is the answer, 50 is the answer. Yeah, so sorry for the cut. Basically what happened was the battery of my mic was like totally gone, so then I tried to re-record it, then I forgot to press the recording button. So all of these are happening to me. So this is the third time actually I'm recording this. So yeah, what I was discussing was like I had already written few things, so I will just explain the written things what I have written, right. So this was the first thing that I was writing, right, is bandwidth generally r by L is in radian per second, but if you want to mention in hertz, you have to divide by 2 pi. You have to remove the radian basically. It will be 1 by seconds. So to remove the second unit, you have to divide by 2 pi. So this you have to keep in mind, right, if they have asked in radians or in hertz. Cool. Now I know bandwidth is r by L. So I have a r by L over here, right. So r by L is bandwidth and I have a extra divide by 2. So this will be bandwidth divided by 2. This also will be bandwidth divided by 2 whole square. Plus what is this? 1 by under root LC whole square. 1 by under root LC is omega naught, right. So this is omega naught whole square. Same in case of omega L, just here there will be a negative sign. So I can actually write my final formula for the higher cutoff frequency and the lower cutoff frequency as plus bandwidth by 2 and minus bandwidth by 2 plus under root bandwidth by 2 whole square plus omega naught whole square. Okay, this is what I can write, and this is a very important formula that I want you to remember. This is one thing, first point that I wanted to remember. Okay, next what do I want you to remember? Next is this one. If I take the product of these two, omega H and omega L, you will see a very good relationship. Okay, but not all relationships are very good, but this is a very good relationship. Okay, so I was just joking, right? If you are in a relationship, of course, I hope it lasts. So what I was saying is, if I multiply this is A and let's say this is B. Okay, so what will happen? This is A plus B and this is B minus A. So B plus A into B minus A, it will be B square minus A square. So B is this under root thing. So if I square it, I will get back this whatever was inside the under root, right? If I square A under root, I will get back whatever was inside the under root. It is bandwidth by 2 whole square plus omega naught square. Okay, then I have this A square minus A square. A is bandwidth by 2, A square will be bandwidth by 2 whole square. So what is happening? These are cancelling each other out. So I get a very good relation, that is omega H into omega L is equals to omega naught whole square, because this is what omega naught whole square. What is omega naught whole square? That is 1 by LC. So basically the geometric mean of the higher 3 dB frequency and the lower 3 dB frequency is omega naught. It is GM, right? GM of is omega naught. Now there are two cases here. This is the case one. Now for the students who know analog electronics or who know bit about filters, they can listen to this discussion. Otherwise you can ignore. Okay, you can ignore for the next 1 to 2 minutes. So if my omega naught is very higher than bandwidth by 2, that actually means what? That actually means it is a very high quality factor filter. We will discuss about quality factor in the next lecture. Basically my cutoff frequency, not cutoff frequency, my resonant frequency is very high and bandwidth is very low. So it passes very lower band of frequencies. So it is very high quality factor filter basically. So it will only pass very small amount of frequencies. So these type of filters, whenever these conditions happen, right, are known as notch filters. And the higher 3 dB frequency and the lower 3 dB frequency, I can write approximately equals to this. How? If like what is the condition? Condition is omega naught is very greater than bandwidth by 2. Condition is omega naught is very greater than bandwidth by 2. So omega naught is very greater than bandwidth by 2. So let's take bandwidth as 0.5 and let's take omega naught to be 100. So 0.5 by 2 whole square plus 100 whole square. Who will dominate? who will dominate? 100 whole square will dominate, of course, because like this is negligible, right? Almost equal to 0. So this whole result comes out to be almost omega naught only. So that's why I have written here almost omega naught. Now you might have a doubt, sir, why, like you are taking the approximation here. Okay, I agree with you, but why you are not taking the approximation here? This is also small, right? Bandwidth by 2 and omega naught is here. So this is linear. Here we were squaring it. So as I am squaring it, whatever is less, right, that even becomes more lower. Let's say 0.5. If I square it, it will become 0.25. So it is even lower. So that's why I am using the approximation. I am not using the approximation here. And omega L, same approximation you use, you will get minus bandwidth by 2 plus omega naught. What about for the case when my bandwidth by 2 is very large, when my bandwidth is very high? If my bandwidth is very high, it almost acts as a low pass filter. Okay, it almost acts as a low pass filter. This is the frequency response of a low pass filter. So the higher 3 dB frequency is the bandwidth. Because what happens, again I make the same approximation. So this time bandwidth by 2 is very high, so I can ignore the omega naught. So bandwidth by 2 is very high, so this result will almost be equals to bandwidth by 2 only. So for the higher cutoff frequency, bandwidth by 2 plus bandwidth by 2 will be bandwidth. For lower, it is minus bandwidth by 2 plus bandwidth by 2 is 0. So that's why it behaves as a low pass filter. So lower 3 dB frequency is 0 and higher 3 dB frequency is bandwidth. So it passes the, what is the bandwidth of the low pass filter? It is the higher 3 dB frequency only. There is no lower 3 dB frequency because it is equals to 0 only. Okay. So this is the key point. If bandwidth is very greater than omega naught, it behaves as a low pass filter. If bandwidth is less than omega naught, it behaves as a narrow band filter or notch filter. So it's a conclusion, and you will get to learn about this filter in other subjects. Okay. So this was one case. So these were all the written things that I have told you. Like, you can go through, read about this, and this is the ultimate summary. So one thing I forgot to mention is that what is the magnitude of the impedance at the higher and lower 3 dB frequency. I know my Z is equals to R plus J XL minus XC. Okay, and I know my XL minus XC is this, which is equals to plus minus R. Correct. So this value will always be equals to plus minus R at omega H and omega L. So if I square plus R, it will be R square. If I square minus R, it will be R square. So it does not matter if I choose plus or minus R. So here I have R square, here I have R square. Ultimately, my magnitude of impedance comes out to be under root R, under root 2R, under root 2R. So that's why in higher 3 dB frequency and in lower 3 dB frequency, the magnitude is higher, is under root 2R and under root 2R. In resonance, it is R because it is minimum. And in the, what is the phase? I discussed about it, right? For omega L, it is capacitive behavior, so it will be minus 45 degrees angle of the impedance. For omega H, it will be inductive behavior, that's why it will be plus 45 degrees. That's it. Okay. So from here you can go through the conclusion, power factor, all those things. Good. And this is the graph basically. This is the impedance angle graph. So impedance angle will, with respect to omega, impedance angle will vary something like this. Okay. It will vary something like this. And for like omega less than omega naught, it is capacitive in nature. Why? I have explained in this lecture only. For omega greater than omega naught, it is inductive in nature. That's it. Okay. And of course, you can see here like how does the magnitude of the impedance varies and how does the impedance angle vary. So both things we have mentioned. So impedance angle is basically theta v minus theta I. Magnitude will be minimum at omega naught, except that it will be root 2R at omega H and omega L. Okay. So this graph is, we have to here, this way. Okay. So this is not a phasor basically. This is just a representation of the impedance, how the impedance varies basically. So at ZL equals to Z minimum, it is equals to R. At ZL load impedance, ZL equals to under root 2R, it is equals to what? It will be either the lower 3 dB frequency or higher 3 dB frequency. Whenever the magnitude of the impedance, all the results, right, all the results whatever we have derived is for a standard series RLC circuit. If the circuit has been changed, so all these results will be invalid. But generally they ask in this result only. Okay. But remember, if the circuit has been changed, all the results will change. The resonance frequency will change, everything will change. Okay. Just be careful regarding that. So at resonance basically for a series RLC circuit, we know the at lower 3 dB frequency, the impedance angle will be minus 45 and magnitude will be root 2R. At higher 3 dB frequency, impedance angle will be plus 45 and magnitude will be root 2R. Okay. So that was for the lower and higher 3 dB frequency. The power factor I have mentioned. This is not a phasor basically because of course we are varying the frequency, right? If we are varying the frequency, then we cannot represent them in the same phasor. So frequency is changing, right? So that's why these are just some vectors to visually represent how my impedance varies with respect to frequency. Okay, that's it. And of course, at omega naught, at the resonant frequency, my admittance will be maximum, impedance will be minimum, and admittance will be maximum. That's it. Okay, so like I was deriving basically the voltage across the inductor and capacitor at resonance and when it is maximum, when it is maximum, because it does act as a magnifier circuit. How I will explain. Okay, so what we are doing is we are simply applying VDR, voltage division rule, okay, in phases. Basically, I have this voltage source. This will get like all these three elements are in series, so voltage will be divided. So I just simply applied the voltage division rule, like this JXL divided by R plus JXL minus XC. That's it. So magnitude of the voltage VL is equals to magnitude of V. Okay, it is XL divided by R square plus XL minus XC whole square. Okay, 1 by 2. So just I'm discussing about the magnitude. I'm only concerned about the magnitude. I'm not concerned about the phase. I'm not concerned about the phase. So magnitude is something like if I break down my omega L, XL to omega L, and this will be omega L, this will be 1 by omega C. Okay. Now at resonance, what happens? At resonance, omega L is equals to 1 by omega C, right? So this part, imaginary part is gone. So only this part is remaining, right? So this part is omega L divided by R. So omega naught L divided by R, this is actually known as quality factor. The magnitude of the voltage is magnitude of the input supply voltage into the quality factor of the circuit. So this term we will learn in the next lecture. Okay, this term we will learn in the next lecture. So this is what happens at omega naught frequency. You observe that, what do you observe? So before coming to the next point, right, you observe generally, right, quality factor is generally higher than 1. Generally quality factor generally will be higher than 1. Okay, this is, so if that is the case, then my magnitude of VL is greater than magnitude of the supply V. Now is that possible? Because let's say if I have a DC circuit here, Z1 and Z2. Okay, so if I see that let's say this is not a okay, this is a DC source plus minus. Okay, so if this is DC source, if I have input V in, can you tell me, is it ever possible for V1 and V2 to be greater than V in? You will say, sir, are you going mad? How can I get more voltage? If I am giving 5 volts, how can I get 10 volts here? Are you mad? Okay, but in AC it is happening. And have we done anything mathematically wrong? Because I've told you quality factor will be greater than 1 only. Okay, we can choose the values, it will be greater than 1. Have we done anything mathematically wrong? No. Main fact of the matter is, in AC it is possible actually. Why? Because what is happening is that in AC, if I just copy the series RLC circuit, if I have the series RLC circuit, where is the series RLC circuit? Okay, the circuit is very far off. Yeah, here it is. So if you see, circuit was here only. Okay, where I was going. Okay, if you see here, that basically, right, you might have a doubt how, like, voltage is getting divided, right? How can it be more than the input? So this is producing some voltage and this one is actually cancelling it out, because both of them are in phase opposite, right? If this gives plus X of reactance, this will give minus XC, right? Plus XL, this will give minus XC. So what is happening is that current is same, right? So this drop is plus JXL and its drop is VC is minus J into XC. So ultimately the overall voltage, right, is VL minus VC, correct? So it does not matter if it is more. If VL can be more than V, that is fine, but VC is ultimately reducing it. So overall voltage is still V only. That is the beauty of AC circuits. That is the beauty of AC circuits. So this is, the expression is VL minus VC. That's why if VL is very very high, that's fine. VC is also very very high. So both of them are cancelling each other out. Ultimately the result is V only. Okay. This we will see in the quality factor lecture. So like this was the important fact that I wanted to clear out. So let's come to this. So I wanted to find the frequency at which the uh, inductance voltage will be maximum. It is not here. Inductor voltage will not be maximum at omega naught, it will be higher, it will be at some other frequency. For that I have to simply differentiate the magnitude with respect to omega, because I am varying omega, equate it with 0 and then solve. So I will solve it. So I have assumed this, this we cannot assume V, this we can assume to be any variable. Let's say what variable u, okay, let's assume this as u. So this will be u square basically. Yeah, so I had to cut the video basically because like the derivation was going long. So I thought the derivation is not important, and don't worry, that formula, like the result will not be asked in examination, but you should know what is the final result, so that when if you solve a question similar to this, you know what to expect. So what I'm doing, I'm just differentiating my capacitor voltage, right? Inductor voltage, and equating it with 0. So I assumed this to be u, this whole under root thing to be u. So it is a quotient rule, so it will be u square into the differentiation of the numerator into u. So differentiation of the numerator with respect to omega is L, and this is u only, okay, multiplied by u, minus the differentiation of the denominator with respect to omega into the numerator. So what is the denominator? Okay, it is u only. So what is the differentiation with respect to omega? So first, this is chain rule, right? So half will come in front, then I will differentiate the inside. So half u will always be there, half will come inside, half into n minus 1. It is u raised to power half, so it will be half into u raised to power minus half. So that's why it is 1 by u basically, 1 by u. Got it? This whole thing is with raised to the power 1 by 2. So if I differentiate this, half the power will come in front, and then I will subtract 1 from the power, basic differentiation. Okay, so that's why this is u only, because u is under root, remember u is under root, so that's why it is 1 by u. Okay, then I differentiate the inside function. So inside function I have a r square which is independent of omega, so this is 0. Differentiation of this, again I apply chain rule, again this 2 will come in front, then I will subtract 1 from the power, so this will be omega L minus 1 by omega c into 2, and again what do I have here? So this is basically L plus 1 by omega square c. So this will be like differentiation of the inside function. This is L plus, because this is 1 by omega c, this will be 1 by omega square c. Okay, so this is L plus omega square c. So then, right, if I equate this with 0, so after a few simplification you can go through this, the result we get is omega L max, omega square is 2 by c square, 2 by L, something weird formula. So this can be rearranged. If you rearrange, right, it will be omega L max equals to 1 by under root LC into divided by under root 1 minus r square c by 2L. So this is omega naught. So I can write my maximum value of at which the maximum inductor voltage at a particular frequency, the frequency is I can write in terms of omega naught. I can write the frequency in terms of omega naught. That's it. I can write the frequency in terms of omega naught. So this is omega naught divided by 1 minus r square divided by 2L. Omega naught divided by under root 1 minus r square divided by 2L. That's it. Okay, and this is FL max. FL max is equals to F naught divided by 1 minus under root 1 minus r square c divided by 12. That's it. Okay, so do you need to remember this? No, but at least you should know a result like this exists, so that in the examination hall when you will try to solve this kind of question, you know what to expect. Okay, so yeah, no need to remember this, but at least you should know a formula exists for this, that much you know. So the homework for you is do the same for capacitor. So for the capacitor, I will tell you the final result. It will come out to be omega naught into under root 1 minus r square c by 12. Okay, this will be the final result. So ultimately what is happening is that if you see omega c max will happen here, because at this point of time the capacitance will be maximum for certain frequency. Due to that only the voltage will be maximum, and VL max will happen later after omega naught, because of course after omega naught the circuit behaves inductive, before omega naught the circuit behaves as capacitive. Okay, got it? So these are the different frequencies, and this is the omega naught frequency basically. So this is the graph for capacitor, magnitude of capacitor voltage. This is the graph for magnitude of inductor voltage, right? Got it? So basically what do I understand? So inductor voltage and capacitor voltage will be same at omega naught frequency, because they will cancel each other out. There will be no imaginary component, just real component will be present. Okay, so these are the graphs basically. So yeah, just know a graph like this exists. What is the capacitor voltage for different various frequencies? What is the inductor voltage? You can always use this formula, right? To understand the graph mathematically, this is the formula. This is the formula basically with respect to omega. For VL, this is the formula. For VC, this is the formula. Okay, you can vary omega, and mathematically, like graphically, this will, your magnitude of omega will vary somewhat like this. Okay, I hope you got this. But remember, this formula is valid when this formula is valid only if my, like, because here, right, there, like you should check whether your FL max is lower than, or sorry, higher than F naught. It has to be, right, because only for greater than F naught my circuit will behave as inductor, so that you have to take into account. So if that is the case, then this number, right, obviously has to be less than 1, because this whole thing has to be greater than F naught. So if I equate this to be greater than F naught, what will happen? This will cancel. So this 1 minus R square L will be less than 1. So that's why this whole thing has to be less than 1. So this kind of question can also be framed. And what about here? If it is capacitive, right, I know my FC max will be less than F naught, then only circuit will be capacitive. So of course, if it is less than FC max, so I can write here this whole number has to be less than F naught or omega naught, whatever, like, because the 2 pi radian anyways cancels out. So omega naught is cancelled. So basically 1 minus R square C by 12 has to be greater than 1. So both of these have different conditions, right? This, for in case of capacitor, this has to be greater than 1. In case of inductor, this has to be less than 1. Okay, that you have to keep in mind. Sorry, yeah, sorry, this has to be greater than 1, and this has to be, yeah, no, in both cases we understand that this is always greater than 1, right? Sorry, what I was talking, in both cases here as well, this denominator num, this has to be greater than 1, then only it will be less than F naught, right? Sorry, it will be greater, it has to be greater than F naught, so it has to be less than 1. Okay, it has to be less than 1. Yeah, yeah, sorry. So for it to be greater than F naught, this term has to be greater than less than 1, correct? So F naught by 0.1 will be 10 F naught, so then only it will be greater than F naught, correct? If it is, let's say, 1.1, it will be lower than F naught, right? No, that is what we do not want that. We want it to be greater than F naught. So this has to be less than 1. In this case as well, it has to be less than 1 actually. Okay, I'm sorry. In this case as well, it has to be less than 1, because FC max is here. If I replace omega naught 1 by √2 minus whatever this value is, it has to be less than F naught. So F naught gets cancelled. So this 1 minus R square 2 by L has to be less than 1. So a MSQ can be framed from this basically, that what is the inequality. So this always will be less than 1. This term will always be less than 1. 1 minus R square C by 12, this always has to be less than 1. So this is very important conclusion. This one, if you can somehow know it to remember, just understand some condition like this exists. Okay, just keep this in mind. So basically, what is the range of my FC and FL? So FC will always be, FC max will always be, if I have enough space, I will write here, right? FC max will always be less than F naught, will always be less than FL max. You can replace F with omega, that is also fine. Okay, so that was it about this lecture. So this is the resonance and what are the voltage characteristics. All these are written, like what voltage magnification happens at resonance, why I have explained, right? With a DC circuit and AC circuit, I have already explained. So in resonance condition, XL will be equals to XC. Also the susceptance will be equal. The susceptance will also be equal. So if I write this thing, that 1 by XL is equals to 1 by XC, these are also saying the same thing basically. My BL, inductive susceptance, and the capacitive susceptance are both equal. Okay, so that also you can relate. So that was about it for this lecture. In the next lecture, we will learn about quality factor, and I will give you few homework assignment questions, and we will try to solve few questions, because in this lecture we did not solve any questions. Mainly we learned about the theory of resonance, basics of resonance. So I hope you have enjoyed this lecture. If you did, make sure to hit the like button and make sure to comment down below which part you enjoyed the most in this lecture. Until then, happy learning.